Hi everybody, new chapter, new you, this time. Okay. Well, I don't know how much it will be new, but we'll be looking at trigonometry using right triangles and right angles, which maybe some of you already had already done in previous classes. If you've seen trig functions before, a lot of them see them in terms of right angles first before they talk about unit circles. Okay, so just to remind you, of course, that an angle corresponds to a unique point on the unit circle, and then we say the x-coordinate's the cosine of theta, y-coordinate's the sine of theta. Okay, and this is a circle of radius 1. Now we can also draw a circle of an arbitrary radius centered at the origin of radius r, and if we take the angle here, well, we'll get a new point. This will most likely be different from this point, okay? And this will have an x and a y coordinates. And maybe we don't know what this is, but what we can do is we can call this if this is x and this is y, and we can draw a triangle here, make a triangle out of this. Then this distance will be y and this distance will be x. Okay, and similarly we can draw a triangle here where this side is sine theta and this side is the cosine theta. All right, so before we go on, hopefully you've seen that these two triangles are examples of right triangles. And a right triangle is just a triangle with a right angle, and a right angle is just a 90-degree angle, or in radians we'll say pi over 2. Okay, so, and we usually, this little square here just indicates that these sides are perpendicular, so we're talking about 90 degrees here when you see a square like that in the corner. And just remind you the Pythagorean theorem is all about right triangles. It gives a relation between the two legs of a right triangle and its hypotenuse. If A and B are the lengths of the legs and C is the length of the hypotenuse, then a squared plus b squared equals c squared, something that you should have seen in Math 128, if not other classes. And that's the Pythagorean theorem. There are lots of proofs of that, and we won't worry about that right now. Now the thing here is, if you've seen other geometry courses, you might have heard about similar triangles. And if we say that two triangles are similar, if some combination of sides and angles are maybe not the same, but they're proportional to each other. In this case, these two triangles here, they're right triangles, and they are similar in the sense that all three angles are the same. That is, we have an angle here that's theta, the angle here is 90 degrees, and of course whatever this angle is, this is going to be 180 minus theta minus 90, right? Because we know that from basic geometry, the sum of the angles of all three angles of a triangle has to be 180 degrees. Okay, if you remember that from basic geometry. So the angles here would be 90 degrees theta, and, well, I guess this would be 90 minus theta. And then this is also theta, 90 degrees, and this must be 90 minus theta. Okay, so these the angles are the same. So these angles, they're not equal, but they're proportional. In other words, they're similar. They're similar triangles. And with similar triangles, then that means we can see that the ratios of corresponding sides must be equal. That is, in particular, if these angles here, so here are the angles here. We already said that this distance from here to here is the cosine, and from here to here is the sine. So here I've taken this triangle and I've kind of blown that up, and I've taken this triangle and I've blown this up. Okay, obviously not completely accurate, but they're proportional. And so what this means is that this side, since this is what we call the opposite side, because it's opposite the angle theta, and this is what the adjacent. So we can say that this side divided by this side must equal this side divided by this side. Or another way you can think of that is that this side divided by the hypotenuse, it must be equal to this side divided by the hypotenuse. Or this side divided by the hypotenuse must equal this side divided by the hypotenuse. That's what we mean by similar triangles. So what we get is, in particular, we get sine of theta divided by 1 must be equal to y divided by r. And the cosine of theta divided by 1 must equal x divided by r. And that's how we get these two equations here. And then here we can just cross multiply, and we get y is equal to r sine theta, and x is r cosine theta, right? So that's what this x now, we can say that this is now going to be r cosine theta, and this is r sine theta. Okay. All right, so with this in mind, now we can actually express the sine and cosine as the ratio of these sides. We see that, well, from here, the sine is going to be we said that y was the opposite. Maybe I shouldn't have crossed this out here. The sine is going to be the opposite divided by the hypotenuse, and here the cosine is the adjacent divided by the hypotenuse, right? So x divided by r. So from here, we get that sine of theta is opposite over the hypotenuse, and the cosine is the adjacent over the hypotenuse. Okay. And then because the tangent is the sine divided by the cosine, we can just take the opposite, or we can write the opposite divided by the hypotenuse divided by the adjacent over the hypotenuse, and this is the same thing as the opposite over the hypotenuse times the hypotenuse over the adjacent, and then this is just going to be the opposite over the adjacent. Okay, so because sine theta divided by cosine theta is this equals this, and that's why the tangent of theta is the opposite over the adjacent. And then for the cosecant of, the cosecant is just the reciprocal of the sine, so we can just take the reciprocal of this, and we get the cosecant of theta is the opposite over or the hypotenuse rather, divided by the opposite. And the secant is the reciprocal of cosine, so it's the hypotenuse over the adjacent, and the cotangent is the reciprocal of the tangent, so this is going to be the adjacent over the opposite. Okay, so this is another way. These are the formulas that you might have learned in some other classes when you were learning about trig functions. And of course, this really only works if theta is between 0 and 90 degrees. All right, if you have a triangle like that. Okay, so with this in mind, let's go and do some examples. So in this case here, so it should be possible to find. We have 3 pieces of information. We should be able to find the other 3 pieces of information. So we should be able to find all 3 sides and all 3 angles. Okay. In this case, here's a kind of a well-known triangle. If the hypotenuse is 5 and this adjacent is 4. We can find out what this side is by the Pythagorean theorem. If we just real quickly call this x, we can see that x squared plus 4 squared has to be 5 squared, right? So x squared plus 16 is 25. So x squared is 9. So x is 3. Okay, so this is 3. Okay, and then we can find the trig functions as follows. We'll have, so the sine is going to be the opposite over the hypotenuse, so that's 3/5. The cosine is the adjacent divided by the hypotenuse, that's 4/5. The tangent is the opposite over the adjacent, it's 3/4. And then the cosecant, the reciprocal of the sine, which is 5/3. The secant would be 5/4, and the cotangent would be 4/3. Okay. Now, if you really wanted to find out what theta is, you could just use your inverse. You could just take that theta would be the inverse sine of 3/5. Okay, and you can figure out what that is, but we're going to worry about that now. Okay, but you can just worry about you don't have to worry about ranges, because theta is going to be between 0 and 90 degrees in all these examples, so you can just directly take the inverse trig function if you wanted to do that. Okay, let's look at example 2. Here we have, we can do the same thing we did above. Let's call this C for the define this side. So we know that 4 squared plus 9 squared is equal to C squared. This is 16 plus 81. So this is 97. All right. And it's a good thing I checked, because my notes are wrong, but this is correct, I think. And, okay, so that means, oops, yeah, so actually this is C squared, so this is 97. So C squared is 97, so C is going to be the square root of 97. Okay. All right, so then the sine of theta will be 4 over the square root of 97. Okay, and we won't worry about rationalizing things right now. Cosine will be 9 divided by the square root of 97, and the tangent will be 4 divided by 9. And then the cosecant is the reciprocal of the sine, and the secant will be square root of 97 over 9, and the cotangent will be 9/4. Okay. All right. Example 3. Now here the angle is known and one sides are given, and that should be enough for you to find out what the other two sides are, as well as what the other angle is. Okay. So in this case, we know that with 12, the length of the hypotenuse is 12. So we want to use a trig function that involves the hypotenuse. We can use either the sine or the cosine. It doesn't matter. But if we use sine, we know that sine of theta will be the opposite side divided by the hypotenuse. So the sine of theta is b divided by 12. So b is going to be 12 sine theta, which is 12 sine of 28 degrees. Okay, and then make sure your calculator is in degree mode now, or make sure of that. And then when you do that, this turns out to be approximately 10.6. We're only going to use 1 decimal point right now, because accuracy really isn't the point of this. And then so that's B, and then A. Well, the cosine of theta is going to be a divided by 12. So a is going to be 12 cosine of theta. And this turns out to be, okay, I think I got this around. This is 10.6. And the 12 sine of and sine of 28 degrees, that's 5.6. Sorry about that. Looking at my notes the wrong way. Okay. And we should say, if we wanted to find what this angle is, we could just take, we know that this we take 180 minus 28 minus 90. And this is going to be, so it's 90 minus, this is going to be the same thing as 90 minus 28, which is 62 degrees. Okay, so that this would be 62. Okay, if we ask for that. All right. Another example here. Let's see, that's a little bit. here we have another case, except here the known side is the adjacent. So if we're going to use some trig function that has to be involve the adjacent. Why don't we use it, make it the cosine? So we can see that the cosine of theta is going to be 17 divided by hypotenuse, which is c. We can so we get that the cosine of 55 degrees is 17 over c. We can multiply. We can cross multiply, I guess, or just multiply by c. And then c will be 17 divided by the cosine of 55 degrees, okay, which is 29.6. And then, what about the part B, or to find what B is? Well, this is the opposite. Okay, so we want to use the sine, right? The sine of 55 degrees will be B divided by 17. And sorry, this should be the tangent, sorry. Tangent is the opposite over the adjacent. So B is going to be, so multiply by 17. Okay, and then this tells us that B is approximately 24.3. Okay, so that's how you find B. And then, of course, you can find out that this angle, what does this angle have to be? Well, if this is 90, this is 55, this angle has to be 90 minus 55. And I believe that is 35, right? Okay, so this angle would be 35 degrees. Okay. Last example, if we wanted to, let's say, now we actually get to see some trigonometry in action in real life. Surveyors use a lot of trigonometry. Let's say if you wanted to find, here we have a survey here, which is measuring the height of a building from 1,900 feet away. And let's say we're using the surveyor's machines and instruments, he figures the angle of elevation is 75 degrees. And if you wanted to find the height of this building, well, the height of the building is really the opposite of this right triangle here, where the adjacent is 1,900 feet. So we're trying to, if we call this h, the height h, this is the adjacent, this is the opposite. The trig function we want to use is the tangent, right? So we get that the tangent of 75 degrees would be the opposite over the adjacent. Okay. And then that turns out to be so h is going to be 1900 times the tangent of 75 degrees, which is approximately 7,090.9 feet, I guess. Okay. All right. One other thing, this was not in your book, in your notes rather, but it was in your book. I might not put the angle where you think it should be. I might give you something like this. Let's say this is 62, and I were to give, let's say if I said that this was 3, and this was C, and this was A, I'd want you to find find A and C here. Well, since A is opposite this angle, A is opposite 62 degrees, so this would be the opposite, and this would be the adjacent. Okay, so in this case, so particularly we have the 3 divided by C would be the cosine of 62 degrees, and also that A divided by C would be the sine of 62 degrees, right? And then the tangent would be A divided by 3. Okay, so in this case, we could from here we could get that C would be 3 divided by the cosine of 62 degrees. And from here, A would be 3 times the tangent of 62 degrees. Okay, and you can, if you want to, you could go ahead and plug, find this on your calculator. Again, from here, what we could do is we basically take the reciprocal of both sides. Okay, maybe I should have included this intermediate step. So this would be 3 over C, or C over 3 equals 1 over the cosine of 62 degrees. Okay, and then multiply both sides by 3. Okay. All right. The last thing we want to talk about, you've probably seen this, maybe you've seen this before too. A couple terms. An angle is acute if it's between 0 and 90 degrees. And if you have two acute angles, alpha and beta, and if they add to 90 degrees, then they are called complementary. Okay, and that's what these angles are. Any two angles, any two non-right angles inside of a right triangle are going to be complementary. That's what we've been using. This alpha and this beta have to add up to 90 degrees. And because of that, we have these nice relations between the trig functions. Okay, the sine of alpha is going to be the cosine of beta. Well, why is that? Because the sine of alpha would be B divided by C. Okay, it's the opposite over the hypotenuse. But B is also the adjacent angle of beta, right? So this is the opposite with respect to one angle is going to be the adjacent of the other angle. So this is the adjacent divided by the hypotenuse for beta. So this is going to be the cosine of beta. Okay, and similarly, the cosine of alpha would be A divided by C, but A is the opposite of beta. So this is going to be the sine of beta. Okay, and that gives that. And now you kind of see where these names come from. The CO is kind of short for complementary. All right. The way to think about the cos is like the complement of the sine, where actually the cosine is the sine of the complement of alpha. Okay. Similarly, the cotangent. By the way, you can check that the tangent of alpha has to be equal to the cotangent of beta, and the secant of alpha is equal to the cosecant of beta. Okay, and this just goes back to the just knowing how these the ratios of the sides, right? So that's where the CO stands for. Where you think where did the cosine come from? Where did the cotangent or the cosecant? Well, it's from complementary, and that's because it satisfies these things. So here in this example, okay, so we explained why. The why is because of this, what we just said. Then we have some really dumb stuff here. I mean, these look like they're complicated, but once you realize, okay, 47 and 43, these are complements, right? 47 plus 43 is 90, okay? So the cosine of 47 must equal the sine of 43, so therefore this is 0. And similarly, 16 and 74 are complements, and the cotangent and the tangent are complements. So these are equal. So this difference is 0. And similarly, this 8 plus 82 is 90. Okay, so these are the same. So this will be 0. So this is kind of dumb, a dumb thing, but you should maybe be aware of that. All right. The main thing you want to do is get lots of practice, if you need it, with these type of examples. Okay. And there are going to be lots of examples on your homework. Okay, so just practice. Have a nice day, and I'll see you next time.